Hello, my name is Maddie. I'm a fourth year student doing an honor specialization in chemistry, and today I'm going to be talking about gases and laws for your 1302 midterm. So there are three states of matter, solids, liquids, and gases. So in solids, the atoms are locked in position, and the strength of these interactions between the atoms determines the melting point of the compound. And so the stronger the interaction, the higher the melting point is going to be, so the harder it will be to break these interactions. These atoms possess vibrational energy, which increases with temperature, and when the vibrations overtake the attractive forces, it becomes a liquid. In liquids, the atoms are free to move around, but there's still some attraction which keeps them touching. And the substance takes the shape of the container. Each atom takes up more space than when it's in its solid form because of its increased motion. And the solid is usually denser than its liquid form. However, water is an exception for this rule. And at high enough temperature, the attractive forces are overcome, and this becomes a gas. And so atoms and gases have lots of freedom to move around, and they will also fill the container like liquids. And atoms and gases move with translational energy as well. So there are some assumptions of gas behavior that we follow. So one of the assumptions is that the pressure isn't too high. So this means that the atoms of gases have no volume. And we also assume that gas is well above condensation temperature, so there are no forces acting on these atoms. So we're going to talk about a couple of laws. The first one is going to be Boyle's law, which is P1V1 equals P2V2. And so this law states that for a constant temperature and number of moles, the volume and pressure of the gas are inversely proportional to each other. Another law is going to be Charles' law, which is V1 over T1 equals V2 over T2. And this law states that for a constant pressure and number of moles, the volume and the temperature in Kelvin of the gas are directly proportional to each other. So this is going to increase linearly or decrease linearly. And when we combine these laws together, we get the combined gas law. This states for a fixed number of moles, the equation is P1V1 over T1 equals P2V2 over T2. We also have Avogadro's law, which is V1 over N1 equals V2 over N2. And this law states that for the same temperature and pressure, equal volumes of different gases contain equal number of moles. So when we have a lower volume, we have less number of moles, and when we have a higher volume, we have a higher number of moles. So when we combine all of these laws together, we get the ideal gas law, which is PV equals nRT. And so in this equation, R is the ideal gas constant. And so this constant changes depending on what unit your volume and your pressure is in. So you just have to keep that in mind and make sure that you're using the right constant depending on what units you're working in. And also always remember that the unit for temperature is in Kelvin. So for the first practice question, you can pause it if you want to try it yourself, but I'm just going to go ahead and answer this. So we're going to use Charles' law because we're dealing with a constant pressure, so only the temperature and the volume are changing. So we're going to use V1 over T1 equals V2 over T2. And we are given that V1 equals 0.5 liters, T1 equals 291.15 K. So we are given that T1 is 18 degrees Celsius, but just like I said earlier, you're going to have to convert that into Kelvin. And then we have T2 equals 245.15 K. And we're looking for V2. That's our unknown here. So we're going to rearrange Charles' law for V2. So it's going to be V2 equals V1, T2 over T1. And then we'll just substitute our values in. Which gives us a final answer of 0.421 liters. So D is going to be our answer for that one. And then for this next problem, pause it if you want to try it yourself. But we're going to be using the ideal gas law for this one. So we're going to be using PV equals nRT. And so the question is asking if the pressure and the temperature are doubled, what's going to happen to the volume? So if we double the temperature and the pressure, the expression is going to become 2 of the original pressure times the volume, and then you're also going to have 2 of the original temperature there. So that's what your expression is going to become. So then we can simplify this to this. And you have a 2 on each side, so they're just going to cancel each other out like that, which is just going to make it PV equals nRT, meaning that your volume doesn't change because you end up with the same equation that you started with. So the answer is going to be E, the volume does not change. Okay, so moving on to talk about the molar volume of an ideal gas. So this just states that 1 mole of any ideal gas has the same volume at a given temperature and pressure. And so 1 mole of an ideal gas at 0 degrees Celsius in 1 atmosphere, this is called normal temperature and pressure. It's going to be 22.4 liters. So there are some variations of the ideal gas law. So we know that density is expressed as D equals mass over volume, and the mass is expressed as mass equals molar mass times moles. So when we combine these expressions with the ideal gas law, we get molar mass equals density, the R constant, and temperature over pressure. And so we also have Dalton's law of partial pressures, which is going to be pretty important. And so this law states that the total pressure exerted by a mixture of gases is the sum of all the partial pressures of these gases. So we have gas A, gas B, and gas C. And when you mix all of these gases together, the total pressure is just going to be all the different partial pressures added up together. So that's just what that equation states. So we also have mole fractions, which falls under this law. And so at constant temperature and volume, the pressure is directly proportional to the moles. And just keep in mind that the sum of all mole fractions is always going to add up to 1. So this is a good way to check if you calculated your mole fractions correctly. So Dalton's law of partial pressure also talks about the vapor-liquid equilibrium and vapor pressure, so like changing phases. And so vapor pressure is the partial pressure of a gas when equilibrium is reached. At this equilibrium, the rates of evaporation and condensation are equal. Vapor pressure depends only on temperature of the gas, and so at higher temperatures, the vapor pressure increases. And boiling point is the temperature when the vapor pressure of a liquid is equal to atmospheric pressure. So a lower boiling point is going to equal a higher vapor pressure. So this law also covers average molar mass of a mixture. And so this is the weighted average of the molar masses of the different gases in the mixture. So this is going to be the mole fraction times the molar mass of that one gas component. And so when you use this equation, you can find the molar mass average of the whole gas mixture. For gas reaction stoichiometry, this states that when pressure and temperature are constant, mole ratios are the same as volume ratios, and when volume and temperature are constant, mole ratios are the same as pressure ratios. And so there are some typical scenarios. So there's mole volume, which is the reaction is given in moles and the volume of gases are required. That's when you would use that. There's mass volume, and this could be used when the mass of one component is known and the volume of another must be found. There's volume, which is stoichiometric stoichiometric coefficients are proportional to volume, and pressure. So the stoichiometric coefficients are proportional to pressure. So for the kinetic molecular theory of gases, we have 5 assumptions. The first one is that the size of the molecules is negligible. The second point is molecules are point particles, so they only have translational energy, not vibrational or rotational. For the third point, collisions between molecules are elastic, meaning that the energy and the momentum are conserved. The fourth point is that there are no attractive or repulsive forces between these molecules that we have to account for. And the fifth point is that the average kinetic energy of molecules is proportional to the temperature in Kelvin. So we're just going to talk about this fifth point a little bit deeper. And so the kinetic energy is given by this equation where m equals mass and the u equals speed. So u squared is the mean square speed, which can be found by the average of the squares of the speeds of the molecules. So this equation here. And in this equation, the molar mass is going to use units of kilograms per mole, not grams per mole, which you're probably used to. And so the higher the temperature, the faster the molecules move, and the lower the mass of the lower mass molecules move faster as well. So for a Maxwell-Boltzmann distribution, this theory shows the distribution of molecular speeds. So on the left here, we see that molar mass affects speed. And then on the right here, we see that temperature, the effect that temperature has on speed. So for root mean square speed, this is the equation. And for two gases, A and B at the same temperature, you can use this equation. You don't need to account for the ideal gas constant or the temperature there. So effusion in Graham's law. Effusion is the flow of gas molecules at low pressures through pores or pinholes in a container. The rate of effusion of a gas is inversely proportional to the square root of its molar mass. And so lighter molecules effuse faster than heavier molecules. If two gases that have equal partial pressures effuse through a pore, we can use this equation here, where F is the enrichment factor. And so we just have one last question. If you want to pause it and try it yourself, I'm just going to start working on it. So for this, we need to use Dalton's law of partial pressure. And so we're given that the mixture has equal masses of N2 and NH3, and we're told that the total pressure of the mixture is 10 kilopascals. And so we're going to let the mass of each gas be M. And so the moles of N2, we're going to call that. That's how we're going to label it. And so it's going to be the mass over the molar mass of N2, which is going to be M over 28 grams per mole. And for the moles of NH3, we'll call this. That's how we'll label it. It's going to be mass over molar mass of NH3, which is going to be M over 17 grams per mole. And so the total moles is going to be that. So we can fill this in a little bit. Which will give us, you can take the M out of there, which is going to leave you with this expression. And so our N total that we were calculating up there is going to be this when we calculate that all out. And our mole fraction of NH3, we'll label it as that. It's going to be the moles of NH3 over the total moles. So I'm going to head to the next page to calculate this because I'm running out of room. So to calculate the mole fraction, we're just going to fill in this equation. That's a multiplication sign. So that's what we get when we follow that calculation through. And then we want to calculate the partial pressure of NH3. So we will label that as this. So this is going to be the mole fraction multiplied by the total pressure. And so we just calculated that the mole fraction is going to be 0.621. And we were told in the question that the total pressure is going to be 100 kilopascals. And so this is going to give us 62.1 kilopascals. And so if we look back at our answers, the one closest to our answer is D.